Alright, so today I'm going to be explaining this important paper with the title Generative Modeling by Estimating Gradients of the Data Distribution. This NeurIPS paper in 2019 by Stefano Erman. We introduced a new generative model where samples are produced via Langevin dynamics using gradients of the data distribution estimated with score matching. Because gradients can be ill-defined and hard to estimate when the data resides on low-dimensional manifolds, we perturb the data with different levels of Gaussian noise and jointly estimate the corresponding scores. For example, the vector fields of gradients of the perturbed data distribution for all noise levels. For sampling, we propose an annealed Langevin dynamics where we use gradients corresponding to gradually decreasing noise levels as the sampling process gets closer to the data manifold. This is important, decreasing noise levels as we get closer to the manifold, to the data. So score matching is designed originally for learning non-normalized statistical models based on IID samples. We repurpose it for score estimation. Using score as matching, we can directly train a network. This F theta, we can train F theta to estimate the gradient of log P, probability of data, without training a model to estimate P data first. Because the objective, it can be shown that it is equivalent to trace of the gradient plus. So everything is in terms of S. So we can minimize it very easily. Denoising score matching is just a variant of score matching that completely circumvents the trace. It first perturbs, because this is computationally expensive, it first perturbs the data point X with pre-specified noise distribution, and then employs score matching to estimate the score of the perturbed distribution. Of course, in this, when we have discrete data, when like tabular data, like language, like graphs, things are not as easy as this. Of course, they do some continuous relaxation, but theoretically it's not profound the way they do. There is another approach, slice score matching, that I've explained it in a different video. I think a previous video was about this. We project it using these vectors V. So this becomes a scalar, and then this is a scalar. So first we project it. PV is the simple distribution of random vectors. For example, multivariate standard normal. And this term can be efficiently computed by using forward mode auto-differentiation. Unlike the noise score matching, which estimates the score of perturbed data, slice score matching provides score estimation for the original unperturbed data. So we don't work on perturbed data. And then for sampling, we use Langevin dynamics, which is pretty easy to do. So it can produce samples from this probability density P using only the score function. Just using the gradient of log of P, we can just sample X, this recursive update of X. Now this Z is from normal distribution, but look at the coefficient of that, this epsilon. This epsilon is also here, but as epsilon goes to 0 and time goes to infinity, X tilde T becomes an exact sample from P of X under some regularity conditions. And When epsilon is greater than 0, a metropolis Hastings optics is needed to correct the errors of equation 4. But it can often be ignored in practice. And using this equation 4, sampling from that only requires just the score function. So we first train the score matrix and then sample it. So in this picture you see on the left is just a slice score matching, very bad loss. On the right you see same thing, but data are perturbed with the mean 0 and this small variance. Again, on the left you see this is the same picture, but the negative effect of the manifold on score estimation can be seen here. And then here you see on the left you see gradient of log of p. On the right you see s theta. Slow mixing of Langevin dynamics. When two modes of data distribution are separated by low density regions, Langevin dynamics will not be able to correctly recover the relative weights of these two modes in reasonable time, and therefore might not converge to the true distribution. Our analysis of this are largely inspired by 63, this reference, which analyzed the same phenomena in the context of density estimation with score match. Both slice and denoising score matching can train NCSNs, and we adopt denoising score matching as it is slightly faster and naturally fits the task of estimating scores. So they prefer this denoising score matching to the slice score matching. And here, this is the annealed version of Langevin dynamics. The annealed version. You know, here alpha I, that this coefficient is updated using sigma I to, and sigma I defines here, we skip that. Where was this sigma I? It's here. So sigma I is just a positive geometric sequence that satisfies this. And then we return the latest update. Since the distributions are all perturbed by Gaussian noise, their supports span the whole space and their scores are well defined, avoiding difficulties from the manifold hypothesis. So they did experiments on MNIST data set. This is the in painting with annealed Langevin dynamics. Here we have this mask M. M is the mask to indicate, for example, which we have a picture and then some areas are masked. We want to identify, we don't know what it is. So using this mask, we can do this in painting task.